Assalamualaikum warahmatullahi wabarakatuh. My name is Adam Haris bin Ashraf. Today, my group will be presenting on the design optimization of flag column based on cutting plane method. Before we proceed with the processes involving the design optimization of the flag column of the related problem, I would like to introduce my team members. So the first one, we have Muhammad Nur Nazri. The second one, Muhammad Daniel Haikal. The third one is Hafiz Bashiruddin. The fourth one is Muhammad Aiman Hakim. And the last one is me, myself, Adam Haris bin Ashraf.
I will continue this presentation with problem background. The problem background for this project is to design 9-meter length flagpole that could overcome wind gusts. The design must meet with safety factor, and to save the cost of material, the optimized mass can be calculated by using cutting plane method. Next, I will continue with problem statement. The problem statement is to find the optimized mass of hollow column using cutting plane method. The assumption that have been made to simplify this project is the column is assumed to be elastic, which means the column will return to its original shape after deformation. Next, the column is assumed to be subjected to a static load caused by the wind gust, which means the load is only applied to single direction only. Next, wind gust is assumed to be a deterministic load, which means it can be predicted using mathematical model. And finally, wind gust is assumed to act in the same direction as the long column axis.
To calculate the optimized mass of the hull column, the volume of the hull column should be known, then multiplied with material density. Substituting the given information inside the volume equation will yield the objective function for this problem. We will get the objective function as shown, and the constraint function we will get that as shown.
So this is the flowchart for the cutting plane method, where we have to add the x node as the variable, as the objective function is in nonlinear programming. After that, we will find the new constraint, where the formula is as given. The new is equal to x node minus with the objective function. And then we start with our first step, where we initiate the value for the search space, and also with the termination value. After that, we start to calculate the constant variation at the x, which is equal to 1. This is also the initial value that we estimate, where the point is 0, 0, and we insert the value into the constraint to find the constant variation, and we choose the g with the maximum or the highest value of the constant variation. And then this is the termination factor, where when we get the g max is lower than the termination value, so we terminate. Other than that, we proceed with the step where we calculate the new constraint uh, using the given formula. And then we get the formula and we update the value of k, and then the loop or the next iteration will be done, where we will get the x2 from there, and after that we proceed with we repeat the step again until we find the termination factor. So this is the algorithm for the cutting plane method, where the first one we add the artificial variable x naught as the objective function is nonlinear programming, and then we set the g new equal to x naught minus f functions, We set the termination value, we set k is equal to 1, we set the initial point of x1 where 0, 0, 0. Then we do the graphical method to find the optimal point of the constraint, and then we set for the initial search space. After that, we find the Gmax at point x1. Then we terminate if the Gmax is lower than the termination factor, and we go to the next step if the termination factor is not fulfilled. So we calculate the new constraint with the given formula, and then we update the value of k, and then we repeat the step 6 to 12 until the termination factor is fulfilled.
Okay, for the result, we have a 3D graph of objective function and the constraint function. The purpose of this graph is to visualize the objective function and constraints in order to identify the feasible and infeasible regions of the problem. Feasible regions are those that satisfy all the constraints, while infeasible regions violate one or more constraints. So this is the graph of the problem in 2D, which is including the objective function and the 4 constraints, such as deflection constraint, bending stress constraint, shear stress constraint, and the thickness constraint. This graph helps us to initialize the initial point for the solution so that the iteration can be as minimum as possible.
The final output we will get the objective function is 8.7056 times 10 the power of negative 16 with the iteration count is 76 with the initial gate is 0.
As for the conclusion, we are able to optimize the mass of the column that was subjected to 380 miles per hour wind gust using cutting plane method. And then more on that, we are also able to understand the algorithm behind the cutting plane method while using MATLAB engine. On top of that, we observe that the objective function's value is very small than the expected logical outcome involving the reality of the mass of the column. Given that the objective function is very much dependent on the d0 and di under multiple constraints regarding the algorithm for the problem with cutting plane method. So, for example, we can add constraint that correlates with the deflection of the pole called slope constraints. So, when we add even more constraints, the problem will get more accurate results, especially in order to determine the value of the related objective function. That's all from us. Thank you.